the two Daves that spoke earlier, Dave from Intel and then Dave from the Berkeley Energy Group, set up the topic fairly well, right? Cores are cheap. How you connect them is important, whether it's on chip or off chip for that matter. And heterogeneous computing is something that is quite interesting in most of the applications that we're looking at. So quick overview, I'll give you a quick update on the technology. I won't spend very much time there since many hands went up. I'll give you a real quick snapshot on where the technology is used today. And I'll spend a little bit more time on why I'm here and why it's relevant to this community. And then we'll talk about the various task groups that are in flight within the rapidIO.org community and what the companies who are involved in the technology are investing in and why. So maybe just to get everybody's attention, there are more 10 gigabit per second RapidIO ports in the world than there are 10 gigabit per second Ethernet ports. Anybody believe me? If you pull out your 4G LTE phone and give me a call on my 4G LTE phone, wherever the tower is nearby, the base of that tower, the base station electronics in that tower, whether it's Alcatel-Lucent, Ericsson, Nokia, Huawei, ZTE, Great Dragon Telecom, doesn't matter. RapidIO is the fabric that interconnects the processing elements in the base of that tower. And you go, okay, that's a base station in a cell tower. How many cell towers do you drive by on the way to work versus how many data centers you drive by on the way to work? And multiply that all over the world, right? So from an economic standpoint, to Dave's point earlier, the embedded world and the architectures associated with embedded systems, the economies of scale that have been achieved there are pretty entertaining. So RapidIO as a volume standpoint is doing quite well in the marketplace, specifically wireless interconnect, and we'll talk about that in a little bit. A couple of interesting things that are going on within the community. One is, which I'll talk about later in this session, that is a 64 bits coherent scale-out task group for ARM server class processors. We've got a 25 gig per lane spec that's being worked on right now, and one of the inherent benefits of RapidIO is it's a true fabric. I've got a comparison chart here, and by the way, I'm not a RapidIO bigot or anything like that. Different fabric technologies have different characteristics and different features, and in and of themselves, they each do things very, very well. If Express can solve your problems, you should use it. If InfiniBand solves your problems and it solves different problems than does Express or RapidIO for that matter, then you should use it. Or if Ethernet solves your problems, then you should use it. Pretty standard fare in terms of what the specification stack looks like. PHY level, transport level, and logical level, and they're all independent of each other. Probably the most important thing is there's no host bus adapters associated with RapidIO. All the protocol is terminated in hardware. Here's sort of the requisite sort of check-in chart in terms of the things that it does well versus some of the things that you might be more familiar with. And I could spend a lot of time talking about this chart. I'd be happy to do so, offline afterwards or what have you. But it's a very interesting fabric and a very interesting technology. We talked about latency earlier. If you go back to the cellular infrastructure use case, when that air data is at the tip of the antenna, you have a finite latency budget with which to process those signals, clearly. You don't get to ask for the data again, right? So RapidIO has been historically used in systems where performance critical computing is important, where you have a very finite low latency budget that you need to hit. And typically your compute infrastructure, generally speaking, is heterogeneous, where you have different architects or different processor types or accelerators in a system. The requisite sort of who's who in the zoo. Lots of interesting companies participating in the standard. By the way, the RapidIO standards are completely open. Sorry.
On the previous slide,
Yes.
why does InfiniBand get a red X for latency?
Well, in the scale of what we're talking about, right? So sub nanosecond latencies in RapidIO.
Same for data.
Same for the, we get other metrics.
Yeah.
I'll change that to a green dot immediately. Hold the phone. See, that's why it's a good thing to come and share these things, right? So yeah, so requisite sort of who's who in the zoo kind of logo charts. Lots of companies that I think you recognize, and many of which are very, very active in the standards body. All of the RapidIO specs are open in that you don't have to be a member to use the technology. Once the specs are ratified, voted on, and put up on the site, they're available for download by anybody. The only part of participation, or the only part of membership that you get is you get to participate in the task groups that are forming these specs and clearly vote on the outcome of these specs. And we'll talk about the task groups later. So some market stuff. I'll start here because I think it's most interesting to most of the folks in the room. Certainly when the RapidIO technology was developed originally, it wasn't really targeted at this space. But what we've seen in the last sort of 18 to 24 months is many of the inherent characteristics of the fabric, very low latency, deterministic throughput, hardware managed, hardware terminated protocol, and so on, were interesting characteristics in this space as well as the embedded space that we'll talk about in a second. And we've had a number of folks join, and we'll come back and talk about the ARM64 coherent scale-out task group in a little bit. But we've had a number of folks join over the last year to participate in this work. Maybe the most interesting, or at least public, system that I can talk about and you can go learn more about is this. I think everybody in here is probably familiar with HP's Moonshot platform. This is a ProLiant cartridge called the M800, which includes 4 TI Keystone 2s on a cartridge. Each Keystone 2 has 4 A15 cores and an octal set of C66 DSPs. And you can put 45 cartridges in a chassis, and they're all interconnected on a 2D RapidIO Torus. And this is in production, being used in analytics at PayPal. And there's PayPal's very vocal about how they're using it and why they're using it. And there's more literature available and behind this if you want to learn more. Talked about the comms infrastructure space already. On the industrial automation side, probably the two most interesting examples are in wafer processing, actually. Applied Materials and ASML, arguably the two biggest stepper and wafer processing guys in terms of the equipment vendors. Their systems are all RapidIO based. And then in the mil-aero side of the world, organization called NGSIS, Next Generation Space Interconnect, has selected RapidIO as the fabric for next generation space systems. It's heavily used in defense applications, radar processing, signal processing, and so on. So it's a very interesting technology across a bunch of different market segments. Okay, so the bulk of what I wanted to talk to you about is coming up here in the next few slides around the different task groups that we have in flight. And as I said, in order to participate in these task groups, you need to be a member in the organization, which obviously we always welcome more members. But in order to realize the benefits of the spec work that comes out of these task groups, you don't have to be. Once the spec, as I said, is voted on and ratified, it's available on our site. So this first one here is a task group that actually is turning out to be attracting more than just ARM-based architectures. And there's a few more members that are in the process of joining that are not ARM specific, but different processor core architectures that want to leverage the work that we're doing here. If you had a keen eye when I put up the specification stack earlier, you saw that there was a globally shared memory spec in the stack. And that was built into the original RapidIO stack some 10, 15 years ago, defining a CC NUMA-based Stanford Dash coherency scale-out over RapidIO. And there were a few PowerPC devices back in the day from Motorola SPS that implemented it, but it was not widely used. That spec, that GSM spec, is being sort of taken off the shelf and mapped over to the ARM AMBA protocols for coherency. So that's taking AXI4 and ACE coherency extensions off chip through a RapidIO fabric. So it's a very active task group. This is a group, the list of companies that were the group that started the task group work. They're very active in the work that they're doing with, this is a little bit hard to read, but you'll be able to see it in the slides later, but talking about the use cases that are interesting. And 2P, 4P, sure, okay, our ARM 64-bit server class device is really going to take a toehold in this space. We'll see. It's entirely possible that they will, but it's entirely possible that they won't. But I think most of the interest around the work that's being done here is in heterogeneous scale out. So having, whether it's packet processors or algorithms embedded in FPGAs, different classes of hardware, all wanting to share, whether it's lookup tables, some set of data in a coherent fashion managed in hardware without the need for software intervention. And that's what you can see most of the use case scenarios there are built around. So that's our coherent scale-out task group. The other task group that's very active is, excuse me, is a software task group where we're doing kernel enhancement work, fabric management work, and data path work. And all of this, I'm sure, sounds extremely familiar to most of the folks in this room. A couple of diagrams to show the work that we're doing at the kernel level, at the RapidIO stack level, and sort of the out-of-scope application area. And I'll skip over this next slide here and just go here. So part of the reason that I'm here is the folks at System Fabric Works are part of the RapidIO community and are looking at how to leverage the software task group work that's been done within RapidIO and marry that with the work that's being done here in OffiWig and be able to, such that we're able to use RapidIO as an underlying transport underneath the OffiWig work. And what we're interested in, obviously, is any other OFA developers that want to join the fun. More folks in the playground is always more entertaining. But excuse me, I'm just recovering from a cold. So, we welcome the System Fabric Work guys into the community. So that, as I said, they've just recently joined, and we'd be interesting to see if there's any others who want to join us. I think Dave mentioned a comment about mileage may vary when you're integrating IP, off-the-shelf IP from different chip vendor guys and so on. One of the things that we're trying to do within the RapidIO community is address that challenge and create an open source verification environment for RapidIO endpoints. So we're not giving away in any way, shape, or form the IP. There's IP vendors out there. But if we can create, if you will, a pre-silicon version of the UNH interoperability lab, that's obviously a lot more valuable to the silicon guys than a post-silicon interoperability lab. So the intent here is that We already have a BFM that is UVM based. We take that BFM, we're augmenting it with the extensions that were added for the space profile that I talked about earlier, as well as the 64-bit coherency work, and then surrounding it with test benches and test suites from each of the member companies to create a golden standard, if you will, verification platform. So this task group's pretty active and is proceeding quite nicely with the work that they're doing. I mentioned earlier the 25 gig per lane. Most rapid I/O ports are at least by 4 wide. So this is our 100 gig plus PHY task group, leveraging the existing industry work around industry standards around 25 gig, and that this task group actually is a relatively new task group that's been started up, and in fact, I think they just are going to start their meetings next week or the week after, and clearly we'd welcome additional participation there. Something that's new is, like most standards, we have sort of this burgeoning use of the technology in different research labs and universities around the world. And the Indian Institute of Technology, IIT Madras, and ITU Copenhagen are collaborating on some interesting storage-based work, SSD storage-based work, leveraging Rapid I/O as a unified fabric. So we're in the process of building on that work. There's a bunch of companies that I can't really mention just yet, but commercial entities both on the storage side, the OEM side, and on the silicon side, who will come together working with IIT Madras and ITU Copenhagen to form this task group around storage around using Rapid I/O as a unified fabric. And so they're proposing to take our baseline 3.0. They'll probably start with 3.1, but our baseline spec, optimizing that for larger packet sizes, and APIs optimized for SSDs and non-volatile memories. So this will be some very interesting work for sure. And one of the things when you think about building larger scale systems with I/O complexes, storage complexes, and processing complexes, some of the characteristics of Rapid I/O make it actually ideally suited to be a unified fabric between those subsystems. And this isn't anything that sort of we did, like I said, at the beginning of the technology many years ago, but is something that has been recognized in with different folks coming to the table and participating. And with that, I think I've got a few minutes for questions, if there's any. Sure.
Just a very brief one. Do you want to have content API available, storage API somewhere formalized and available? Or is it like an ongoing process?
That's an ongoing process. So the question was, is a storage API formalized and available? And not yet, right? That's an ongoing project that's being worked on right now, and any input, I'm sure the team would love to have any input into that process if you were interested.
So, what do you use currently for like communication API? Do you have a set of Rapid I/O style communication primitives or things? Or?
Yeah. So if we go back up to that chart, so these are all MPI, RDMA, sockets-based drivers and APIs that have been developed specifically to take advantage of the hooks and protocols that are in Rapid I/O. And part of the work that we're happy to have the System Fabric Works guys at the table. Part of the work that we want to do is understand how much of that can be leveraged into the OFIWIG work, because that I think then starts to become pretty interesting. Anybody else? So my last name's O'Connor, and I would be remiss if I did not wish everybody a happy St. Patrick's Day today. I struggled somewhat with wearing the Rapid IO uniform versus wearing something green. And Kevin reminded me that when your last name's O'Connor, you don't have to wear anything green. So thanks for your time, folks.